In last video, we discussed that electric current can produce magnetism, and it was observed by Oersted. But value of that magnetic field was given by Biot-Savart law. So today, this is the application of Biot-Savart law, that you have to find magnetic field at axis of current carrying circular coil. So there is a circular coil in which current is flowing. Let I be the current flowing through this circular coil, and this be the center, and its radius, let its radius is a, small a. So this is your current carrying circular coil, and you have to calculate magnetic field at its axis. So I will just make an axis at which you have to find the magnetic field. So let P be the point at which you have to find magnetic field. So this is the point on axis of current carrying circular coil at which you have to find magnetic field. Let its distance be x from center. So from center, its distance is x. Now what you have to do, you have to mark few current elements, or say length element, in which current is flowing, due to which there would be magnetic field at point P. See, this whole ring is contributing towards magnetic field at this point. So I'm not taking the whole length of this ring, I'm just taking two small length elements. Let their length be dl. I'm taking two small equal length elements dl. Obviously current is flowing through them, so they're also contributing for the magnetic field at point P. Now join these lines. Now what would be distance? This distance would be, you can calculate by Pythagoras theorem, that would be r square plus a square, and this would also be that same only, r square plus a square only. Let this angle be phi, let phi, and this would be also be phi only. Fine. Now at this point P, there is a magnetic field due to dl, there is a magnetic field due to this dl also. What would be direction of these two magnetic field? If I draw, let this be due to this dl, this magnetic field, I would give name to it db1. Okay, I'm giving name to it db1. The magnetic field due to this length element would be like this, away. Let this magnetic field be db2. Now what would be value of this db1 and db2? Which law I would use? I would be using Biot-Savart law. Now db1 is magnetic field due to this length element, right? Formula is mu naught 4 pi idl sine theta by r square. So mu naught 4 pi I, length is dl sine theta. Now what is theta here? If you see, angle here would be 90 degree, sine 90 by r square. Now r is distance between this length element and point P. That is under root r square plus a square. So r square, this square root would be removed. This is your first equation, or I say value of db1. Now if I want to find value of db2, I want to find value of db2, I would again use Biot-Savart law, and that would be, value would be mu naught 4 pi idl sine, again 90 degree, r square plus a square. So db1 and db2 are same by magnitude, they both are same, but by direction they are not same. So what I need to do, I need to resolve these components. This is the resultant magnetic field due to this, so I have to resolve this. So one component would be of dB1 would be dB1 cos phi, another would be dB1 sin phi. Similarly for dB2, dB2 sin phi, and dB2 cos phi. So these are components of dB2, dB2 sin phi, dB2 cos phi. Similarly for dB1, if I resolve component, there will be two component. So this would be dB2, dB1 sin phi, and this would be dB1 cos phi. Now, as we can see, dB1 and dB2 are exactly same in magnitude. So dB1 cos phi, this is dB2, dB2 cos phi, and dB1 cos phi would be same in magnitude. As you can see, they are in opposite direction and also same, so they cancel out each other. So the effect due to these two components is zero. So the magnetic field coming here is because of component dB1 sin phi, dB2 sin phi, and there would be many more length elements here, like these two. This whole is an element, this whole ring is a length element. So the component that is contributing for magnetic field at axis is dB sin phi. See, dB1 sin phi, dB2 sin phi, there would be many length elements like that. So for finding the total magnetic field, what we can do, we can integrate any one component, either dB1 sin phi, dB2 sin phi, over this whole ring. What I want to say is, if I want to find magnetic field at axis, that is net magnetic field, I have to integrate only one of the component, dB1 sin phi or dB2 sin phi, over whole ring. Now the minimum length of length element can be 0. That can be the lower limit. The upper limit is, that is maximum. The maximum length of this ring can be 2 pi r, that is circumference. Here we don't have r, we have a. So the upper limit can be 2 pi a. So by integrating this component dB sin phi over whole ring, over the length of whole ring, that is from 0 to 2 pi a, I can find magnetic field of this current carrying circular coil. So I will just put the value here and solve. So B is equal to, if you put the value 0 to 2 pi a, mu naught by 4 pi ideal, sin 90 is 1, you don't need to write it again, r square plus a square into sin phi. Now you can find value of sin phi in this, from this triangle. Sin is perpendicular by hypotenuse. So this is a by under root r square plus a square. R square plus a square to the power half. I can write half. This is value of sin phi. You can take the constant outside. So what you get, B is equal to mu naught by 4 pi ideal. You cannot take out dl outside. Dl is variable. R square plus a square to the power 3 by 2. So you're left with integration of dl, right? Integration of dl from 0 to 2 pi a. Now what is the integration of dl? That is L. And then you will use limits, that is upper limit minus lower limit. So if I put the value, so it would be mu naught 4 pi ideal r square plus a square 3 by 2. Integration dl becomes L and limit 0 to 2 pi. Now you can put value of upper limit minus lower limit. That would be 2 pi a minus 0. That is again 2 pi a. So the value is B is equal to mu naught I 2 pi a 4 pi r square plus a square to the power 3 by 2. You can solve 2 pi. This can be cut it and made 2. So formula would be mu naught I a 2 r square plus a square to the power 3 by 2. This is the value of magnetic field due to current carrying circular coil at its axis. Now here can be some cases also. For example, if you want to find magnetic field at surface, now surface of that coil, not here, you want to find magnetic field at here. So the value of x in this game becomes a. This would be a only. Distance would be a. So in this expression only, what you can do, you can replace x or r by a. By mistake, I have written this as r squared a square. So let this be r. Okay. So r becomes a. This was r from O to P. But if this P point shifts here, so this would be a only. So you can replace r by a, and you can solve a square plus a square becomes 2a square. 2a square 3 by 2. This would be magnetic field at surface. Now suppose you find magnetic field at center. Now this point when comes here, distance would become 0. The value of r becomes 0. Now again you can fill value of r with 0 and you can solve. So a square 2 to cancel become a cube. You can find it yourself. This is just simple maths. So what you have to do after doing this, you have to do for two cases. This is your homework. You have to find magnetic field at center also and at surface also by just replacing value of r. When you're finding at surface, r becomes a, and when you are finding at center, the value of r becomes 0. So this is the way you can find magnetic field at axis of circular current carrying coil.